Okay, and I will share my screen. This is April 20th, 2026, 9:42 a.m. Pacific time. Let's take a look at the syllabus. Okay, here go here the syllabus. I just discovered, right? A student of yours. Who was that? Was this? She was Stefan, right? Stefan. Stefan warned me about that. Kehayan. Here you go. There is a paragraph there in the syllabus that was not supposed to be there. An item there, and this one number 9 on the lab report. In the past, laboratory report. In the past, I used to require my students to turn in a hard copy, and and today I don't do that anymore, and I forgot to delete this part from the syllabus. Okay, there's no hard copy, just the spreadsheet that you turn in for the lab. Okay, and here's the calendar. We had the exam. Today is the 20th of April, the 18th meeting, the 11th week. Okay, we are covering chapter 22. But before we continue covering chapter 22, let's talk about the lab report that I uploaded to your group folder, okay? Let me get a sample of a lab report from a previous course. So you know how to follow. So the first thing that I want to do while I look for this lab report sample, I want you to download the correction of your lab report, either one or two, okay? So the correction is a PDF file, like I mentioned in the announcement, right? The correction is a PDF file in your group folder. The title of the PDF report is, the PDF document is P07L01 for lab 1, right? And group XX.pdf, where XX is the 2-digit group number of yours, and P07, P07. Let's copy this one, that's better. L02, PDF. Download the correction of your lab report. The correction is a PDF file in your group folder. Okay. And it's kind of straightforward to read, to decipher. It's kind of straightforward to decipher the correction. I wrote a computer program to do exactly that. That's why I require you to do all reports in the spreadsheet. And let me get a sample from a previous semester. (2026), right? 2025, where is spring report, lab correction. Let's get lab 01, spreadsheets, corrected folder. I have a bunch of those here. Let's see. Yeah, here you go. That's lab number 1, okay? Here you go. So your lab report should look like that. How much this guy got? This person, this student got 82% in the lab report. Okay, here's my copyright symbol, right? You know, everywhere where you missed something, there is a color code, with the exception of this line. This line here doesn't mean anything. You didn't miss anything here, okay? Let me get this student in. It's not nobody here? Okay. So in this case, this student didn't put the volts, meter, meter, volts, meter, meter, and so on, right? And if you miss a unit, you have this red color code there in your lab report. And the color code is right in here in this table at the bottom. See incorrect units is in red color, right? The student didn't put the proper unit. If you miss any of the significant figures, it's going to be in the bluish color. Let's take a look at the bluish color. Yeah, here you go. This student missed this significant figure here. Okay. Like I said, this violet color is nothing, okay? That was something that I used to have in the past, but then I decided to remove from the activity. And what else? Is the cell that has this color, not the numbers. If you have added unnecessary numbers, right? The cell would be green. Okay, the cell would be green. Note C that this student, he missed 2 significant figures, definitely. Okay, but my computer at that time didn't pick up the 2 significant figures here. Okay, I picked it up only now. I noticed there was a bug there in my program, and I fixed that. Okay, here's the color for if you missed the R square, for the CL, for the slope. Okay, and no resolution is no longer. And then, you know, things like graph 1 and graph 2, I have to do manually. I have yet to write an equation, a computer program to correct the graphs automatically. And there is what else? The graph labels, right? You gotta put the graph labels there. The title of the graph and the units, that's what I call the graph labels. Okay. So that's what you have to know, okay? And for each thing that you miss, you have the points here that I take out, okay? 1 point for each incorrect unit. In this case, was 0.6 points for the significant figures that were missing. For your lab report, I adjust that to 0.3 to give you more points, okay? Those are the points that I'll be subtracting from your lab report. That's what I'm summing up here. So that's how I do my correction. This guy, you know, summed up the total 18 points that he missed. 100 minus 18 is 82. And then this number 82 is automatically recorded right here at the top. Okay? That's how you should read the correction. No, don't forget, right? Students usually forget to put the units here. It's so easy to do that. All you have to do is to copy and paste, copy and paste, copy and paste, right? Student, I don't know why. You know, maybe you're in a hurry, you don't want to spend too much time with the lab report, and you don't put the units there. But it's something very, very simple to do. Gonna spend a little bit more of time. See, the student missed also the units here. Meter, V, meter, meter. Here would be the number 1 because it's a unitless unit. This student got the CL. That's why the CL is not marked with a color. Okay, the CL color would be this color here. Okay, is that clear? So that's how you should look at the correction of the lab report, and make sure you don't do the same mistakes in future reports. All it takes is time. Okay, all it takes is time. Many of the tasks that you're going to do during your professional life is going to take It's going to take time to do them. It's And that's what this lab report is all about. It takes time to do the things, and that's how we do in professional life. We have to document the proper units of measurement when we are in the lab, okay, or even in the floor factory, the factory floor, right? Factory floor, floor of the factory. So, any questions about that? So open there your, let's see, what's this one here? Okay, this one is one of the students, okay, of the course. Let's see lab number 2. Each lab has a slightly different way of grading. Lab number 2. Again, I'm getting the corrections of last semester, 1 year ago. Here you go. Lab number 2 looks like that. Notice that this student didn't put too many significant figures, right? That's why he has green all over the place. So sometimes you have to zoom in to see see everything clearly. Yeah, here you go. This grade was 65%. And this student put too many digits, right? He was supposed to stop right in here, the 3rd decimal place. But this student put 2 additional decimal places for the X. And what was the name of the student? I don't see. Oh, the name is right in here at the title of the document. And here you go. The student missed the unit for R, unit of R. Okay. Put a unit of volt for the sigma. Didn't put any unit for the sigma divided by R. Okay. Green color all over the place. So the student managed to get the CL. Right? And here is the color code, what the color code means. Okay. He missed some points in the graph units and labels. Just 1 point. 0 all over here, right? No points we missed. And optimization of the graph, very important. Very important to optimize the graph. I take out points for the optimization as well. Okay. And if you sum everything, I'm taking out 34 points, almost 35 points. And the student got 65%. That's for lab number 2. Okay. So close it. Okay, so to decipher the correction, so what you gotta do? 1, open your corrected lab. 2, look for the color code at the bottom of the document. Okay. What are the color code? Here you go. In general, okay? In general. Sometimes I vary the color code in general, In general, let's put it this way. In general. Red is for units. for missing units. B. What else? Light blue is for missing sig figures. In general, right? What else? Green is for significant figures that were incorrectly added. 3B, and then color code for the CL. What that color was? Brown, right? Looks like I chose a brown. No, it's not a brown. It's some other type of color. Let's take a look there. Yeah, this one is violet, right? Violet is for CL. Oops. See, violet is for CL, and so on. Okay. And if you read completely the syllabus, I discussed that in detail as well. How let's see here. Okay. Correct number, see, right here in this. The correct number of significant figures for each missing significant, I will subtract 0.11 points from your lab report, right? For each significant figure that's added incorrectly, I will subtract 0.1 to 0.5. Use of proper units in the report. For every missing or incorrect unit, I will subtract 2 to 3 points. Actually, it should be 1 to 3 points here. In this report, I subtract only 1 because we have so many significant figures in there. Let's correct that. 1, yeah. Version 7. 1 to 3 points. Okay, proper format, neatness, completeness, and accuracy, reporting of proper statistical results, average standard deviation percentage difference, right? For each incorrect value, I will subtract 1 to 5 points. Average standard deviation percentage difference, blah, 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 right? I will subtract 1 to 5 points. The graph must be clean and planned to optimize its space, no large blank areas in the graph. You must label the axes of the graph with their respective quantities and their corresponding units between parentheses. For each missing incorrect labels or units, I will subtract 1 to 2 points, right? That's how I correct the lab report, okay? It's all documented here in the syllabus. Having said that, now we can go back, right? And continue with what we're doing. Mutual inductance and self-inductance. Okay. So the definitions of mutual inductance and self-inductance comes from the Faraday's law. Okay. The consequence of these two types of inductance, the consequence of these two types of inductance are the result of the Faraday's law. Faraday's law. It's just another way of writing Faraday's law. Let's here you go. Writing, and let me also, it's very important. Let me do that here for you. I'm going to here write those three equations, right, for the capacitance, resistance, and the inductance in a different way. Okay? I'm going to write that down in terms of delta Q over delta T. Okay? And here you go. I'm going to write that down at 1 over C, right? 1 over C is what I once called my incapacitance. Remember that? I once called that incapacitance. It's going to be delta Q over delta T. But here, this delta in this case, because it's going to end up being a Q, I'm going to raise my delta to the 0 power. Okay? So you can see the progression of this equation. Delta to the 0 power and delta T to the 0 power is going to be delta 0 Q over delta T to the 0 power is going to be Q. Okay? You see the progression? The simplest device is the capacitor. The delta T has a power of 0. The next device that's simpler is the resistor. It has the delta term has a power of 1. That's a nice way of remembering this equation. And for the mutual inductance, not just for the mutual inductance, but also for the self-inductance, okay? And the self-inductance we abbreviate by the letter L, we have the second power here. The Q appears in every one of those. And can you remember that? The M, what's the M? The M we derived before. And don't forget, this thing comes, what you see right here comes from Faraday's law, okay? Comes from Faraday's law. Don't forget that Faraday's law, how is Faraday's law spelled out? The equation for inductance okay, comes from Faraday's law. And what was that? It's going to be minus number of turns, delta, it's not delta Q, it is delta delta pi. Okay? Because my phi has a magnetic field and the magnetic field is directly proportional to the current, that's why we end up with a delta I over delta T here. Okay, here's the same as delta I over delta T. Okay, and the mutual inductance equation that we derived before last class, going back here, is given by this term right in here. Okay, and I'm going to remind you exactly what is each parameter. Mutual inductance. N prime. What's N prime? N prime is the number of loops of the secondary inductor. N is the number of loops of the primary inductor. L, lowercase l, lowercase l, lowercase l is the length, of the primary inductor. Everything with prime is related to the secondary inductor, and everything else without the prime is related to the primary inductor. Is the area of the secondary inductor, is the area of the secondary inductor. Okay, here we go. Okay. That's for mutual inductance. And we are doing all of that for the coil, for the solenoid. Don't forget, this is for the solenoid. For self-inductance, the derivation is similar, but the final equation is going to be different. So for self-inductance, let's take a look here. I'm gonna get an illustration, right? The slides, not lab, right in here. Electromagnetic induction. I showed you mutual inductance before. Let's go back here. It's better, quite quicker, right? Here you go. That's mutual inductance. This guy is inducing a current in the primary coil, the primary solenoid is inducing a current in the secondary solenoid. But if you have just one solenoid that is being powered by a generator, don't forget a generator generates a current that varies in time, the current bounces back and forth. What's going to happen? This inductor here will induce a current in itself. That's the important difference between mutual inductance and self-inductance. Not only is capable of inducing a current in a secondary solenoid, but it's capable of inducing a current in itself as well. That's going to counter the change of the actual current being powered by this generator. That's the symbol of the generator. Generator that we studied, okay? So here you go, right in here, here's the solenoid, right? Cross-section of the solenoid. The current is moving back and forth, back and forth, back and forth, back and forth, right? Just like you saw right in here. Because the current is moving back and forth, the magnetic field is also moving back and forth, changing in time. Let's say it starts pointing to the right, maximum intensity of the field, start decreasing, becomes momentarily zero, and then invert direction. When it inverts direction, the current, that was because the current inverted direction. And the current, during all this process, the current is also decreasing. Not just the magnetic field is decreasing, but the current is also decreasing. That's why the magnetic field is decreasing, because the current intensity is decreasing. The speed of the charges is decreasing, right? The speed of the charge in the wire is decreasing. Look at this arrow here. This arrow here tells you the size of the current. And then the current change direction, it starts increasing, right? Starts increasing, reaches a maximum value, then it starts decreasing again. Okay, and because of this increase and decrease, because of this change in the magnetic field in time, the solenoid is going to induce a current on itself that's going to oppose the increase in the magnetic, that's going to oppose the change in the magnetic flux. Okay? Going to oppose the change in the magnetic flux. I'm going to document everything that I'm saying. Okay? Here you go. If the magnetic field is decreasing, the magnetic flux is also decreasing. Consequently, the induced current in this solenoid is going to be in the same direction as the regular current in the generator. Okay? It's opposing the change in the magnetic flux. Now, as the current changes direction, okay, the magnetic flux is going to increase. As the magnetic flux increases, the induced current must go against the original current. Okay? That's what Lenz's law is all about. That's what Lenz's law is all about. Let's do that. Here you go. Let's write that down here. Here you go. Delta B at this point in time is maximum current. It's a solenoid current. At this very moment in time, I can write that down for you. Let's see. Insert equation. Let's get this equation here. Good. At this very moment in time, delta B, delta, oops, wrong, delta B over delta T is momentarily zero because the field reached maximum intensity, okay? Consequently, the induced current must be zero. Okay? If the magnetic flux is zero, the induced current must be zero. Because the induced voltage is zero, the induced current must be zero too, right? Delta B equal to zero. Let's see here. I'm going to put something else here. At this instant of time, B is maximum. Max intensity. Oops, he doesn't like it. He likes just max. Okay, now I add the X here. Max. Not just, it's maximum, but the current is also maximum. The current of the generator reached its maximum value as well. And now the current should be written in lowercase, right? Current should be written in lowercase because we have a AC circuit, alternate current circuit. At this instant of time, the change in magnetic field is going to be momentarily zero. Consequently, the magnetic flux the change in magnetic flux is going to be zero as well. If the change in magnetic flux is zero, according to Faraday's law, the induced voltage, what happened here? Here you go. The induced voltage is going to be momentarily zero as well. Induced voltage is directly proportional to delta B, delta T, right? And because the induced voltage is zero, the induced current is also 0. I gotta put that in. Okay, let's put it like that. Induced voltage is also 0. Let's move down like that. Next, in this next one here, current is not maximum. Current is less than its maximum value. Consequently, the magnetic field. Yeah, let's put, here you go, let's put in a better notation here, right? Here you go. I is equal to maximum. Better notation. B is equal to maximum at this instant of time. I call that instant of time 0, right? Delta B, delta T is equal to 0 because it reaches its peak. It's momentarily 0. This slope, right, is a sinusoidal curve. So the change in delta B, the change in the magnetic field with time is going to be momentarily 0. Because the change in magnetic field is 0, the change in magnetic flux is going to be 0 too. According to Faraday's law, the induced voltage is going to be 0, and the induced current is going to be 0 as well. Okay? So let's go back to the other one. Here we go. B is less than maximum. Delta B, delta T is going to be negative because the magnetic field is decreasing. Delta phi, delta T is going to be negative. Okay. Delta, here you go, this V induced is going to be different of 0. I'm not going to put it negative. It's not going to be negative because don't forget, we still have that negative sign, right? So we can say that V induced is greater than 0. It's greater than 0 by virtue of the Faraday's law. And the density and the current, the induced current is also going to be greater than 0. And now I'm going to draw here the induced current. By induced current greater than 0 means that the current points in the same, the induced current points in the same direction as the original current, induced current. Like that. Okay. Is going to be the same thing for the rest. While this current is decreasing, right? The situation doesn't change. The only thing that changes is going to be the intensity of the induced current. Okay? And by the way, I'm gonna, here you go, here, right in here. Let's see the next one. Okay, we are about to turn 0, right? At this very moment in time. Okay, the induced current in the same direction. And then when it changes direction, right? Now let's see here. Here the current here is approximately zero. Write that down, approximately zero. So you can picture that. Oops. Oh, not that I want. This max here is not supposed to be here. Approximately zero. It's about to become zero. And if the current is about to become zero, so is the B about to become zero as well. The B is about to become zero. But not the delta B delta T. The delta B delta T is going to be maximum. It's going to have a maximum value, okay? Maximum value. At this very moment in time, delta B delta T is going to be maximum, and so will the delta flux. So it has a logical progression, right? Here you go. Writing here delta B is zero. Then it keep on delta B keep on increasing. Don't forget the delta B over delta T, right? Let's see here. Increasing in magnitude. I mean, increasing in magnitude. Okay, it's a negative, but increases in magnitude. Increases in magnitude. How am I gonna put that here? Let's put equal to minus maximum value. Let's put this one, minus maximum value. Okay. And the induced voltage is also a maximum value because it has to do with the slope. That's what delta B delta T is all about. It has to do with the slope. Okay, here is gonna be maximum. Gonna put let's put Vmax. Better notation, huh? Oops, it doesn't like that. Here you go. Now he will accept my maximum. My induced current is going to be maximum as well. Max. Because it's about to become zero. Okay. So it evolves in time like that, right? Let's see. And then it switches direction. It switches direction. Now, delta B is not decreasing. Delta B, let's see here. Let's see. I maximum. Let's put I less than zero. Like that. Right? I less than zero means that it changes direction. Less than zero. Okay, but now, because it changed direction and it's increasing, now my delta B delta T is increasing. If the delta B delta T is increasing, the flux is increasing as well. And because the flux is increasing, now the induced voltage is going to be negative, and the induced current is going to be negative as well. See the direction of my induced current here? Here's my actual current, here's my induced current. Okay, I'm even going to put the I symbol there next to this guy, so you know it is the induced current. Okay, like that. like that. Okay. And the whole thing, continue increasing, right? The magnitude of the magnetic field continue increasing until it reaches a maximum value in the opposite direction, right? Something like equal to, not here, but right in here, equal to minus B max. Minus B max. Here is going to be equal. Did it reach max? Yeah, now it's decreasing again, right? I minus I max. I max. At this point in time, because it reached a maximum value, the delta B, delta T is 0 again. The delta phi, delta T is 0. This is 0. And the induced current is 0. Okay? So I can write down my illustrate my induced current right here. Induced current right in here. Right? Let's see here. Induced current, okay. Now my induced current is going to be 0. So I'm gonna shrink this guy to the point that you don't see anything, right? This is kind of a vector. Very small vector. See, it's out of phase, right? It's out of phase with the magnetic field. When the magnetic field is maximum, the magnitude of magnetic field is maximum, the induced current is minimum. It's out of phase. We call that out of phase. The regular current is not out of phase. The regular current is in phase with the magnetic field because it's directly proportional to it. And here you go. That's and then it decreased, right? And everything repeats again. Now that it's decreasing, right? It's like what happened before. And the induced current changed direction. Okay, that's what's happening here. If you do the mathematical calculation for the mutual inductance, which is the same the same derivation that we did before, okay? For mutual inductance, comma, the equation is similar to the above one. With the difference, we replace n prime and a prime with n and l, since there is no secondary solenoid, right? Since there is no secondary solenoid, let's put this L in italic so you don't think it's a uppercase I. And the self-inductance we represent by the letter capital L. That's why I'm using lowercase l here, right? Usually you use uppercase L for the length, right? But in reality, I saved the uppercase L for the mutual inductance. N prime becomes N, A prime becomes A, right? And we end up having something like that, n squared here. But this equation can also be represented in a different way. Most books sometimes prefer to represent in a different way, not as n squared, but a lowercase n to represent n divided by L, by the length. That's the density of, linear density of turns. Okay? We usually put the mu naught at the beginning. Let's put the capital N here, right? Mu naught is at the beginning. Okay, mu naught is at the beginning. Let's put the mu naught at the beginning. Beginning. And we do the same here with the mutual inductance. Here you go. Like that. Both the mutual inductance and the self-inductance have the same units. Okay? Both M and L have the same unit. And what's going to be the unit? Okay? What their units are? Let's take a look. Unit. See, you have mu naught here, you have mu naught there. You have n that has no units whatsoever. N square here, we have n square here that has no units. Area, L. So they have exactly the same units. Both L and M have the same units. And let's take a look at the units of L and M. Unit of mu naught. Unit N and L. Okay, this guy here has some units. Is divided by N, divided by meter, right? This one also has a unit. Capital N doesn't have a unit because it's just the number of turns. It's an integer number by itself. Yeah. This one is going to be 1 divided by meter. This other one is going to be meter squared. And this one here, we have to look at the internet. What's the unit for this mu naught, right? Let's take a look at the unit of mu naught. Okay. Unit of magnetic permeability of free space. Henry per meter, but I want the actual unit. Here you go. Tesla, let's see, express newtons per ampere squared. The SI unit for magnetic permeability, Henry per meter. I don't want the Henry per meter now, which is also expressed as Newton per ampere square. Okay. Or Tesla meters per ampere. Okay. So it has different units, different ways of expressing this unit. We didn't talk about the unit of Henry yet. So let's stick to Newton per ampere square, which is the same as Tesla meter per ampere. Tesla meter per ampere. Oh, or kilogram meters per second square, right? Kilogram meter divided by ampere square. That's the base units. That's the base units. You can go even further, can change the ampere to coulomb per second, right? Newton, let's stick to Newton per ampere square. Admit Newton per ampere square. like that. Meter cancel out with meter, right? Meter square cancel, we get something like that. Now, this unit shows up so frequently in physics that we give it a name. This unit is so important that we give it a name. We call it the Henry. Okay? So let me write that in terms of the main units, right? It should be kilograms meter per second square. I'm gonna put second square here. Ampere is going to be coulombs per second, like that. That's the main SI unit, meter combined with meter, with this meter here. This second square cancel out with the other second square that's here. We are left with Coulomb square. So now we have the base units. Now we do have the actual base units. Much simpler, right? Than the other one that he showed to us. Much simpler, kilogram meter square per Coulomb square. Okay? He didn't convert the amperes to coulombs per second. So I like that. Okay, these units show up so frequently in physics that we give it a name. We call it then the Henry, honoring Joseph Henry. Henry. Or H. Henry. That and that's the Henry is the unit of inductance. That's 940, right? No, 1040. Henry is the unit of inductance. So, I want you to do the following, just to practice that at home. Do exactly what I did here for the rest of those drawings, right? Exactly what I did here on the right side and the left side. Okay? So you can understand, can practice that and understand better, right? In this specific case, just repeat what I did, right? If I do everything for you, let's see here. We can do more than that. Let's see. I'll leave this way. I'm not gonna do more than that. Let's have our break. It's 10:40. Any questions about that? So break 10:40 a.m. to 10:55 a.m. And then I see you in 15 minutes. Oh, someone asked a question before we go for the break. You cannot see. Oh, Susan Acosta cannot see the corrected lab? Really? Okay, let's see. What group number are you, Susan? Group number 2. Let's figure that out. What's going on? Group number 2. I'm going to download. I saw your message only now, Susan. Otherwise, I had replied before. Let's see here. 2026. Troubleshooting, right? Group number 2, physics 7, group number 2. Group number 2. Okay. Okay, yeah, you have group number 1, right? Did you download this one, Susan? Yes, okay. Did you see the grade, everything in there? Yeah. No, you didn't see the grade here? Let's see. Let's download it. Can I show your if I open the document, everybody's gonna see your grade here. Can I do that? Oh, it's fine. Okay, so here you go. So here you go. Here is the spreadsheet. Here's the document that you're supposed to visualize in PDF. Okay? Do you have Adobe Reader installed in your computer? Can you see something like that? Here you go. I'm going to zoom in. Can you see something like that in your computer? You see it now, right? Okay. So it looks like I forgot to upload your lab number 2. Let me see. Everybody has lab number 2 there. Let's see. Group 1, yeah. No, I didn't. Oh, I didn't upload lab number 2. I didn't upload for anybody. Just seeing that. I thought I had done that. Okay. Very well reminded. Okay, good. Let me upload the correction of lab number 2 for everybody. Okay. I thought I had done that. I was sure I had done that. Let's see here. Lab. Lab raw data, lab correction. Lab 2. Spreadsheets. Let's go. Corrected. Now you're all going to have your lab 2 correction. Group number 1. We have to adjust our break, right? Now we have to adjust our break. Group number 2. Group number 3. Yes, you know those things that you're sure you have done, but then you find out that you didn't do it? That was one of those. Group number 6. Group number 7. Group number 8. Group number 9. But I did log in the grade there, right? Yeah, that what must have happened. I logged in the grade, and then I forgot to upload the spreadsheet, the corrected spreadsheet, the PDF file. You know, I should have uploaded first and then logged the grade afterwards in the grade book. 14, 15, 16, 17. I wish they had a computer program to do those things automatically for us. I wonder if they do. Do you folks know any computer program that allow us to do those things? Drag and drop automatically? I don't know. I don't know any, but there must be, right? So many computer software out there. So now let's go. Our break is gonna be 10:45 a.m. to 11 a.m. Okay, now you can see your correction. And if you have any questions, let me know. Okay, see you in 15 minutes. Mm. Looks like I left my audio on, right? Hope you didn't hear anything while we were in a break. Okay, so let's go back to our notes. And we have mutual inductance, we have self-inductance. And Okay, and now we can say that self-inductance and mutual inductance are the magnetic counterparts of capacitance and resistance. Okay. So by the same token that we have capacitance for the capacitor, resistance for the resistor, and those two are electric devices, we also have their counterpart for the magnetic devices, self-induction and mutual induction. And let's see, let me share the screen first, right? Yeah, here you go. So self-inductance, induction, and mutual induction are magnetic related phenomena. Okay, and the inductor is a magnetic device, so we can say that capacitance, a capacitor and resistors. If capacitors and resistors are electric devices, comma, inductors are magnetic devices because they depend on the magnetic field. That's how they work. And now let's talk about the energy stored in a magnetic in a device. Okay. But let's see. Let me also. We're almost over with this chapter, by the way. Here you go. Let me show you what we have done so far. We are writing here, right? We did induced electromotive force. We did motional EMF. We did the magnetic flux, Faraday's law of magnetic induction, Lenz's law. We skipped 22.6, electric generator. I'll walk you through. Very important device. We are going to be using the electric generator from now on for many of the problems that are going to show up. Mutual inductance and self-inductance. We didn't quite finish because there is one more thing that we have to do. Mutual inductance and self-inductance. What else do we have to do? We have to talk about energy stored in the inductor. Okay. We saw before that electric energy is stored in a capacitor. Okay. Now, in a capacitor, actually, it's not in a capacitor. Okay. It actually stored in the electric field, ultimately, the energy is stored in the electric field, in any electric field of the capacitor. Okay. Now we will see that magnetic energy can also be stored in the magnetic field of an inductor. So here you go. That's a new device that you have to keep in mind. And the inductor is a very simple device. Let's take a look at some inductors out there in the internet. You know, just think about winding a wire in a tube. That's what an inductor is all about. Okay, you get a tube, you wind several turns of wire around it. That's one type of inductor. And this inductor is the solenoid. Those devices are used all over the place. In every electronic device, even in your car, okay? Inductors. Uh, let's take a look at the Wikipedia. Here you go. See, that's an inductor. A wire wound around, and that's the symbol of the inductor, the coil, right? The coil. That's the resistor. Here you go. For me, this is a resistor. This is not an inductor. That looks like a resistor to me. That looks like a capacitor to me. Why did he put inductor here? Okay, but let's take a look at the Wikipedia. Here you go. Different inductors. That's the solenoid. That's the toroid. I do not know which one is this one here. You can see that there is something there inside that we cannot see. Most likely we have some turns of wire here. Here's also an inductor, right? We passed, this is a toroid-like inductor, but he didn't wound everything around it. That's an inductor looks like. And that's the symbol, the electronic symbol, the electrical and electronic symbol for the inductor. Okay. Here you go. Here's the equation. Here is the Faraday's equation, Faraday's law. Okay. The magnetic flux is the inductor times I. I didn't say that, but you can think of the inductance as being inductance times the current as being the magnetic flux. That's another way of looking at it. All right. Don't forget it's B times A, right? B is always directly proportional to I. For the sake of this course, is always proportional to I. And okay, I'm not going to show that because it involves integrals. We can, but the idea here was just to show you some inductors out there. Let's see where we can buy inductors. Where can I buy inductors? Okay, so there are all sorts of manufacturers, toroidal core manufacturer, inductors, electronic components. Let's see if they have any pictures of inductors here. I want to show you some pictures. Oh, all sorts of inductors here. Nice picture, right? Oops. I want to go back here. This one. See a solenoid here. Oh man, can't you just stop? Okay, toroid here. Oh, he's going too fast for me to show you. Let's see if you have any transformers, inductors. Okay. Okay, toroid here. Another toroid. This one looks like a solenoid, two solenoids, one next to each other. This is also an inductor, but it's packaged. Has two leads here. Axial leaded inductor. Another type of inductor, and so on. Those are very important devices. That's why we study that in physics. It's important in telecommunications as well. And now, it's important because it stores magnetic energy. It stores energy that can be used to do some useful work. Okay? The resistor, capacitor stores electric energy. In the inductor, it stores magnetic energy. And the resistor only consumes energy. That's what the resistor does. The potential energy of the capacitor, we saw that before, is what? Is the capacitance, half of the capacitance times the voltage squared. Okay? And when we do the energy store, potential energy, when we say energy, we mean potential energy, okay? potential energy is stored in a capacitor. And we are going to see the counterpart for the inductor. Now, what about this is for stored in a parallel plate capacitor. Let's put here. Parallel plate capacitor. Energy density. The electrical energy density. Energy density is given by that you are not going to forget because it's easy to remember. We derived that in class as well. And now we are going to see what is the potential energy stored by the inductor, stored in a solenoid inductor, and the magnetic energy density of a solenoid, of any inductor, okay? We're going to see that. Here you go, here is gonna be U over B. Here is going to be U over B as well, okay? U over B, lowercase u over B is going to be the amount of energy stored in the magnetic field by the amount of volume. I'm gonna derive this equation. And instead of epsilon naught, here we are going to have mu naught. Can you remember that? If you remember the one for the electric field, you will remember the other one for the magnetic field. It's gonna be like that. Okay? And we can derive that, by the way. And the reasoning is very similar. Let me just give you the final equation. So we can make the derivation after all, after that. Okay, it's going to be, instead of, here you go, what is half becomes half. What is C becomes L, okay? And what is V becomes I. Okay? That's not difficult, right? That's not, if you memorize this one, you're going to be able to memorize this other one. If you memorize this one, you're going to be able to memorize this other one. The only difference is that instead of multiplying by epsilon naught, you divide by mu naught. Yeah, you divide by mu naught. But let's derive that. It's always good to do that. We are going to do that derivation of the first equation. Derivation of the first equation. Okay, derivation of U sub B. U sub B. And is the step-by-step is very similar to what we did for the capacitor. Okay, so just remember that we have the definition of potential energy, right? We have the definition of potential and the definition of potential energy. And the way it goes is like the following. We start with this relation here of delta U over delta Q is equal to electric potential, right? There's a relationship between the potential energy and the electric potential. And we repeat the same for the inductor. It's going to be the change in magnetic potential energy over delta Q. Now is going to be equal to minus the electric potential of the inductor. Okay. Remember, I want to calculate this one, this device, this guy that you see right in here. It's not an obvious derivation, okay? It's not an obvious start, so that's why I'm doing that for you. So here you go. I'm gonna pass my delta Q to the other side. Okay. And then I'm going to boldface the induced voltage. When I boldface the induced voltage, all I have to do is to plug in Faraday's law there. Faraday's law, that's gonna read like L minus L delta I. Don't forget the I must be variable in time, otherwise we are not gonna have the phenomenon of induction. So I'm emphasizing that here for you. Here you go. Delta I, delta T. Faraday's law. Faraday's law in a different format. Delta I, delta T. So the negative sign cancels out. That's the first obvious step that you can see in this equation. Whoa. Okay. But now what we do, we jog this delta T that you see right in here. Okay. We jog the delta T that you see right in here. We put it below delta Q. Like that. Okay. Here you go. Delta Q over delta T becomes I as a function of time. Okay. Here's the change in the current. Here's the current itself. Change in current and the current itself. And what else? What else can we do? We are going to do something else. A mathematical trick. I'm going to pass my delta I to the other side. Okay. And we have this equation. And next step, we plot the left side of the above equation in terms of I of t. Okay. And when we do that, we get a straight line with a slope of L. That's what we get. Make sense? That's what we have here. We need this visualization to see what's going to be the next step. To see what's going to be the next step, okay? Okay, so keep that in mind, that how can you visualize that, right? Okay, you're going to see a very nice way of visualizing the delta U. Here you go. A rectangle with an infinitesimal side delta I, right? Here is I. I get a rectangle here with infinitesimal side delta I. The area of this rectangle is going to be delta UB. It's going to be the potential energy, right? That's something that people found that out for us. something that's not obvious, right? So here you go. We go ahead and when we do this plot, we draw a rectangle right in here with this side delta I. This side here is going to be delta U over delta I. Multiply this side of the rectangle by this other side of the rectangle, we get delta UB. And delta UB is going to be the change in potential energy here in this region for the current. Okay? So we can see that by summing up all the infinitesimal components of those rectangles here along this curve, we are going to get the total potential energy that is stored in the magnetic field. Okay, so the total area of this triangle that you see here is going to be the total potential energy of our inductor right in here. Here we go. Here you go. Get this area, right? This area is going to be what? UB. UB is going to be half of I times delta UB over delta I, right? That is the total potential energy. Okay, but we do know that delta UB over delta I, you already know what that is, right? Delta UB over delta I is what? Is this term here in the equation, is Li. Okay? So substituting Li right in here, I'm going to put it between parentheses so you know it came from that term. We get the total potential energy stored in the magnetic field, Li square, half of Li square. Oops. Nice derivation, just in geometrical terms. So, this derivation was done, right? This derivation was done using geometrical arguments. No need for calculus. No need for calculus. Now we are going to continue our derivation to derive the energy density. Now we will derive the energy density stored in the magnetic field. Magnetic field, okay? We start with this one. And we do with the solenoid. Uniform magnetic field. Okay, so here we go. We started with what we got before. And I'm going to replace the inductor equation, the equation for the inductor. I'm going to use that for the solenoid, right? Every magnetic device has a different equation for the inductance. For the solenoid, specifically, is this one here that we derived before. Is that right? Okay, this one here, I pasted twice. mu naught NP What we want to calculate, don't forget, don't lose sight of what we want to do. We want to calculate the following. We want to calculate delta UB over delta V. Okay, that's what we want to do. Let's not lose that from our side. Delta V, is going to be dependent on the area, right? Make sense? And we can take a slice of our solenoid and we are going to need also the length of the solenoid. Okay, so let's write that down in terms of the length. We have a length of the solenoid here implicit in our equation. And here is going to be what? P stands for primary, okay? Primary inductor. Actually, there is only one inductor there, but it's divided by L. That's what the lowercase n stands for. Lowercase np stands for. I'm going to take out the parentheses. There is no need for the parentheses. Here you go. And I'm going to do the following. A little mathematical trick. I'm going to divide and multiply the equation by L. So I don't change it, right? This L cancel out with this L, right? It's the same equation. This equation is exactly the same as this other equation here. But I need this L upstairs because this A times L becomes the volume. Okay, and this volume, I'm gonna put it lowercase, and then I'm gonna put L squared. Okay. And now this capital N combined with this other capital N, we square it. So I'm gonna simplify my equation. Like that. Okay, becomes NP squared, and then NP squared divided by L squared is gonna be lowercase NP squared. We reduce it to a simpler equation, just like that. And now we can pass my volume to the other side. Potential energy divided by the volume is the energy density. Like that. And we represent the energy density by the lowercase u. We didn't finish yet. We didn't finish yet because we have more to do here. We're still using the solenoid, right? As an example. We're doing that for the solenoid. And recall that there is a relationship between the magnetic field and the current for the solenoid that looks just like that. This N here should be, the N of P that we have in there, the same N of P. And what I want to do, I want to change this current to the magnetic field. I want to write this relationship here with the magnetic field there. Because for the other one, for the capacitor, we had the electric field. So here you go. This one goes to the other side. And I pass this one to the other side as well. Right? And continue here. Like that. I is replaced there inside. And now we are getting what we said we are going to obtain, right? This B becomes squared. This mu naught becomes squared. This NP becomes square. Oops, no. No, the square goes elsewhere. No, boy, again. Like that. Yeah, here you go. No need for the parentheses anymore. No need of the square anymore. The NP is going to cancel out. And so the mu naught we go. I'm going to put the mu naught here next to the 2. Okay, and, or even better, I'm going to do it a different way. Here you go. Like that. I put 1 divided by mu naught, right? 1 divided by mu naught, and I eliminate this mu naught here. For the electric energy, for the density of electric energy, it's like the following with the electric field here. Yeah. Compare those two. They look very alike, very much alike. Okay. So that's the important equations that we have. Let's write that down, right? The important equations so far. The first one is the electric induction. That's the lab. We don't want the lab. Let's see here. 21. No, we don't want that. The first equation is the first important equation is this one here. Faraday's law. Electric induction. Okay. The second important equation is the magnetic flux. Even better, let's see, did I put N in there? I think I did, right? Yeah, I did put N in there. Magnetic flux, the same idea as the electric flux. So there is nothing new about that. We talked about the electric motor and the electric generator. The electric generator in this chapter. All right. Okay, let's here you go. That's the current induced by an electric generator. Okay. Very important too. Not just the current, but the voltage as well induced by the electric generator. The next important equation is this. Not this one. It's going to be the definition of mutual induction and self-induction. Okay, here you go. Another way of writing up Faraday's law. And then we have self-induction as well. What's missing here is missing here the value for M and the value for L. We have also the equation for the potential energy of an inductor. This is the potential energy for an inductor, any inductor. Okay, we derived the potential energy density of an inductor using the solenoid. And there is one important detail about this second derivation. Whatever we got at the end is applicable not just to the solenoid, but to an inductor in general. When we do this derivation specifically for the solenoid, we get that we find that the result also applies to any type of solenoid. Important formulas. Important formulas. Among those formulas, the only one that you have to memorize is this one here. Everything else follows from this formula. That's the most important formula that you have to memorize. We start with this equation. I'm going to just, okay. If we turn a coil with constant angular velocity inside a constant B field, we induce an electric current that changes in time sinusoidally. Okay? Not just an electric current, but also an electric potential. And the electric potential sinusoidally. That's the induced current. That's the very principle of the generator. That is the very principle of the generator. The generator generates a voltage that changes in time sinusoidally, and also an electric current that changes in time sinusoidally, and is the source of a AC circuit. The generator is the source of any AC circuit. Okay? But let's not forget, those two formulas that you see right in here are consequence of this law here. The law and the fact that you are turning a coil inside a magnetic field. And then there is another thing that an important device out there with the inductors, right? And we define something that we call a mutual inductance. This equation depends again on the Faraday's law. Two inductors, one concentric with the other. One solenoid induces a current in the other solenoid. And here is a single solenoid that induces a self current on itself. Okay, the mutual inductance is given by this equation. The self-inductance is given by this other one. Okay, so important equations for an inductor. 1, 2, 3, 4. We find that an inductor stores potential, magnetic energy, which is given by, here you go, half LBI. Now, using the relation for the solenoid, using the relation of between the B field and the current I for the solenoid, comma, we derive the following equation for the density of for the energy density is stored in the magnetic field. Okay. Although the above relation was derived for the solenoid alone, comma, the final result is applicable to any inductor. Any inductor, whether it's a solenoid, whether it's a toroid, or any other solenoid that you can create. Okay, inductor. Whether it's a solenoid, whether it is a solenoid, a toroid, or any inductor geometry that you can create. Like that. And the last chapter now is going to be on transformers. Very important device that you see all over in the streets. Device that I use to power our homes, to transfer energy from the grid to your house. The last section, what time is that? 11:47. Yeah, 11:47. Let's see if we can finish that. The last section is on transformers. Transformers are very important devices that you see everywhere. Everywhere is on transformers. This device transform, right? I'm gonna put it why it's called transform, right? Transformer. Transform transforms current of a given voltage, okay, to another voltage. That's what transformers do. They transform electric current that has a given peak voltage to another peak voltage. Just recall that your generator, let's not forget, right? I didn't plot here for you, but it's important. And let me plot that for you. Recall, right? Recall that generators, oh, it's we derived there. Let's see here. Going down, going down, going down. Yeah, here you go. We derived that equation, right? We derived that the induced voltage of a generator is given by this equation, right? BA omega is a constant, right? BA omega is a constant. So this voltage that you see here is going to have a peak value that's given by this relation that you see right here. Okay, so it's like a sinusoidal curve. So what transformer does, he changes this value right in here from one circuit to another. That's what the transformer does. That's what a transformer does. Change this peak value to another peak value. Okay, it can be either larger or smaller amplitude. Recall that a generator generates the following voltage. Yeah? I'm going to plot here for you using Excel. And let's see here. Let's see here. Go. It's going to be something like that. T, right? Voltage in volts. And let's start 0 seconds. Let's see, a tenth of a second. Third of, and so on. Let's see if we can get a good curve here. And my voltage here, let's say it's going to start at 110, 100 peak 110, just like we have in the power. And I'm going to use use a cosine or a sine there. Let's see what I use there in the notes. I use the sine, right? So I'm going to put a sine here as well. And then I'm going to use, let's try 60 times t. Let's see if it works. It doesn't work, I change it. Okay, so let's see here. Sine, it starts with a negative, it goes to a negative. Interesting. Let's see if we get a nice, no, I don't think we got a nice, we should go 6 hertz. Let's try 6 hertz. No, it doesn't work either. 1. We're supposed to see 110 very soon. Yeah, okay, looks like this one works well. I chose a good frequency for my oscillator. That's what a generator is. It's an electrical oscillator. Okay? And I think I can increase the frequency a little bit more. Let's put twice the frequency, otherwise you're going to have too many points in our plot. Yeah, okay, I think it's better. See, the peak occurs close to 110, right? That's what this equation is supposed to tell us. 110 volts, which is the voltage that we have at home. Can be 220 volts as well. Now it's increasing, right? No, it's decreasing. I want it to come to the point where it's going to. Okay, now let's plot, insert. Okay, that's how the voltage looks like. The peak voltage is at 110 volts. Okay? And what this transformer does, the transformer changes this peak voltage. That's what the transformer does. It changes the peak voltage. It doesn't change the frequency. It changes the peak voltage. So let me copy this device there. And here's I'm going to show you also a picture of a transformer. Okay. Let's see if I have here a drawing of a transformer, even better. By the way, what you see right in here, I already drew a transformer for you, okay? I just didn't tell you it was a transformer. What you see right in here is a transformer too, okay? What you have right here is a transformer. Here is your electrical circuit coming from the outside, right? From the grid. And here is the electric circuit that goes to your home. A transformer is exactly like something like that, although there are other geometries as well. So let's one possible transformer configuration is this one right in here. One possible transformer configuration. Then I'm going to, here you go. Oh, I got one possible transformer configuration. And I have also to copy the voltage of my, I'm going to put chart design here, chart element, axis title, primary horizontal is going to be T, okay? T in seconds. And axis title, primary vertical, voltage in V, okay? Both phase. Bold face. I want to do better than that, but let's keep it this way. Otherwise, it's gonna take too long for me to go into the break, right? Here you go. That's how the voltage of a generator looks like if you are cranking it with a constant angular velocity, right? And that's what most generators are like. And I want to, okay, like that. He called that a generator generates the following voltage. Following voltage variation. like that. An example, one example of a geometric configuration of a transformer is the following one. This one here. Two concentric solenoids. Two concentric solenoids. One connected to a generator. The other connected to the circuit of your home, okay, with no power whatsoever, no power source whatsoever. The power source is the generator of the primary whatsoever. There's no power source whatsoever. That's 12 noon. Think about that. Let's take our break now. And let's see. Yeah, let's take our break now. Then I'll show you another configuration of another break. 12 noon to 12:15 p.m. Right? Any questions about that? Am I missing any messages from you? I don't see it. Okay, so I see you in 15 minutes. I am back. I'm going to share this screen and let's finish this part here. Chapter 22. Okay, so that's one example of a transformer. And you have already seen this illustration before, right? I didn't. The only difference that I didn't tell you that this thing can be considered a transformer, but it does work like a transformer. That's and like I said, transformer are devices that transfer energy from one circuit to another circuit, and it can either increase the peak voltage or decrease the peak voltage. If this guy is operating, if the original generator is operating at 110 volts, when this original generator can be connected to another solenoid, for instance, right? The generator connected to a primary solenoid. Here you go, generator connected to a primary solenoid. This circuit can induce a current in another solenoid. And depending on the number of turns that each of those solenoids have, you can either increase or decrease the peak voltage. That's what transformers do. Okay? So transformers, again, I think I already said that, right? Are devices that can either increase the peak voltage that can either increase or decrease the peak voltage of a original circuit. Okay? And you do that by choosing a proper combination of the number of turns, number of loops, right, in each solenoid. Okay, N prime. Okay. So let me give you another illustration of another solenoid that's used, or another transformer that is more efficient than this one that you see here. Here's a picture an actual picture of a real life transformer. We have something like that there at the college. Okay, it is a solenoid. One is the source, the other is the induced one. The picture doesn't show exactly which one is the source. Okay, the picture doesn't show which one is connected to a generator. Can be either one. By the way, it can be either one, okay? From what I see here, can be either one. So suppose that's the primary circuit here. Suppose this one is connected to a generator. This is a nice, very, very, by the way, convenient geometry for a solenoid. Instead of putting one solenoid inside the other, what people discovered? People discovered that if you insert a metal inside each solenoid and connect them, just like exactly what we have here. See, what you have here is a metal connected one solenoid to the other one. Metal connected one solenoid to the other. And what does this metal do? This metal concentrates the magnetic field generated by one of the solenoids. It concentrates the magnetic field that propagates through the second solenoid and induces the current on the other one. That's what it does. Okay, that's a much more convenient geometry than the other one that I showed you. This is one geometry, but it's not as convenient as the other. We have a metal core. Oops. We have a metal core here that transfer the magnetic field, concentrate the magnetic field from one solenoid to the other one. That's what this core does. We're not going to go into the details, but it is important that you understand that. Okay, so here you go. Picture of a real life solenoid. Real life transformer made of two solenoids and a metallic core to concentrate the magnetic field. Okay, so when you concentrate the magnetic field, the magnetic flux through the solenoid is exactly equal to the magnetic flux of this other solenoid, because those two solenoids have the same dimension. Okay, so here you go. Let's just summarize what we covered here. In words, one way to create a transformer is to insert a solenoid inside another one. However, there is a much more practical configuration that uses a metallic core to connect two separate solenoids, just like the above figure. Most transformers have solenoid of the same diameter and consequently the same area. For this reason, the magnetic flux through the primary solenoid is equal to the magnetic flux of the secondary solenoid. The primary solenoid is the one connected to a power source or generator, whereas the secondary one does not need to be connected to a power source whatsoever, since the primary is transferring its energy to the second one. The secondary solenoid is exactly the one that goes to your house to power your TV, to power your blender, and so on. Okay? There is no generator there inside your house. Remember that? The generator is outside there in the power station. Okay, and it is because of this transformer, right? The transformer is a very important device. Weren't for the transformer, we couldn't put a power station in a very distant place. And that's what we have nowadays. Most power stations are very far away from your residence. And we can do that. We can concentrate all that infrastructure far away from the residence because of the transformer. And then transmit a different type of current, a different type of current that is the alternate current. Transmission of electrical current is done at very, very high voltage. Okay. Here you go. Another one. Transmission of electric current is done at very high voltage in order to lower transmission losses along the transmission line, along the power cables. Okay. The higher the voltage, the lower the transmission losses. The higher the voltage, the lower the transmission losses. Once next to your house, the voltage is converted, the high voltage is converted to a lower voltage, using a transformer. Otherwise, the higher voltage can kill someone at your house, right? We transmit electricity using higher voltage to lower the transmission losses. When it gets nearby your house, we convert it into a lower voltage to make it usable for us and make it safe also for us to use it. The fact that higher voltage AC power can be transmitted along range. This is the reason why we use AC current today in our houses instead of DC current. Okay, there is a very important historic and interesting historical background behind this fact. Back in the 1800s and early 1900s, there was a fight between two camps. Okay, historical. And if you can watch that movie, the current wars, okay, they dramatize this whole incident between AC current and DC current, the current war, 2017 movie. Here you go. I watched this movie. I do not know if you did. This actor is the Mr. Doctor Strange, right, from the Avengers. He portrays Thomas Alva Edison. It was a dispute between Thomas Alva Edison and this other guy here that not everybody knows about, but you will recognize by his last name. We don't talk much about him. We talk a lot about Thomas Alva Edison, but not much about this guy. His name today are in the appliances that we have out there, the Westinghouse appliance. Okay, his name was George Westinghouse. He was in a fight against Thomas Alva Edison to decide which current we were going to use in our houses. This is historical fact, by the way, okay? So there was this fight between the DC current and the AC current, and that was the current war. One guy was suing the other one to find out who would prevail, who would transmit power to the houses. And today we know that the AC power won the war. The AC power won the war of the currents. Okay, so it's a very good movie, by the way. You have to know, but it's important that have the technical background to understand. Here you go. Benedict Cumberbatch, right? The Doctor Strange from the Avengers, is Thomas Alva Edison. Nikola Tesla was also involved in this fight. Nikola Tesla, he associated himself with George Westinghouse. I don't see George Westinghouse here. Where is him? Strange. They don't list Westinghouse here, but they list who they list here. You will recognize this other name here. William Kramer, where is him? Thomas Alva Edison, Nikola Tesla, Samuel Winslow as Tom Holland, right? The guy that did portray Spider-Man. Samuel Winslow was one of the assistants of Thomas Alva Edison. Mary Edison was the wife of Thomas Alva Edison. And J.P. Morgan, you recognize this name, right? You recognize this name, a very famous financier whose name is still are in the news today. J.P. Morgan. J.P. Morgan used to fund Thomas Alva Edison. But where is George Westinghouse? The most important character in the whole movie they didn't list here. I can't believe it. Journalist, Jesus Christ. President Grover, see that? I can't believe it. They didn't list the guy here. Oh, just Westinghouse, but just at the end. It doesn't make any sense. He was the guy that was appearing the most in the movie. Okay, George Westinghouse, Michael Shannon. So nowadays we know that George Westinghouse won the war against Thomas Alva Edison. and George Westinghouse himself associated with Nikola Tesla, right? We know about Nikola Tesla. Nikola Tesla used to work for Thomas Alva Edison. Thomas Alva Edison wanted to electrify the cities using DC power, direct current power. Why did he want to do that? Because he had the patents for DC power. Okay? And Nikola Tesla was working for Thomas Alva Edison and said, no, you shouldn't electrify the houses with DC current. You should electrify the houses with AC power. That's more efficient. And then Thomas Alva Edison fired him for that, right? And then finally he managed to associate himself with George Westinghouse. And he was successful, more successful with George Westinghouse, and managed to win the war against his former boss, Thomas Alva Edison. That's the whole story behind this drama and behind this technology. There was a fight between two camps. Okay, video on the AC camp, the DC camp, and the AC camp. The fight was about who would prevail, powering all houses. Okay, that was the fight all about. So when we increase the voltage with a transformer, when the transformer increases the voltage, the peak voltage, we call it that the transformer is a step up transformer. Transformer that increases the voltage. Transformer that increases the voltage. Or step down. Transformer that decreases the voltage, the AC voltage in a circuit. I'm talking about the peak voltage, right? That's what I mean by increasing the voltage. That's what I mean by voltage. I mean the peak voltage. This is done by using different number of turns in a coil. Okay, so how the whole thing works? Okay, we just use Faraday's law. And so say that you have 1,000 volts AC circuit in a circuit coming from the street, and you want to lower the voltage to 120 volts. You can lower the voltage by using a transformer where the primary coil has more turns than the secondary coil. And there is a mass behind that. Here we go. Here we have, according to Faraday's law, here we have the induced voltage in the primary circuit is given by this relationship here. Don't forget it's the induced voltage. Induced voltage in the primary circuit. Okay? And is given by the number of turns in the primary circuit multiplied by the change in the magnetic flux in the primary circuit. That's what the P is all about. In the secondary circuit, we have a similar equation. Okay, in the secondary circuit, we have, don't forget the voltage of the generator does not get involved here in this relation. Okay, what gets involved in this relation is just the induced voltage of the primary circuit. The induced voltage in the secondary circuit has a similar equation. This comes exactly from the Faraday's law. Number of turns in the secondary, change in the magnetic flux in the secondary circuit. Okay, what is going to be equal? Don't forget the two transformers have the same area. Okay, have the same area. They must have the same cross-sectional area, just like you saw in that picture right in here. Okay, What we are doing mathematically here applies to this type of transformer. It does not apply to this type of transformer here because one transformer has an area different from the other one, okay? It doesn't apply to this other transformer. So what do? We must make, here you go, if the area of the transformers are the same, the magnetic flux will be the same too, okay? Magnetic flux, change, magnetic flux. If the magnetic flux will be the same, so will be the same of the change in the magnetic flux. The magnetic flux will be the same, and the change in magnetic flux will also be the same, right? So here you go. Change in magnetic flux in the primary transformer is equal to the change in magnetic flux in the secondary transformer. And then I just simplify the notation by writing like this way. Okay? I substitute this equation that you see there right in here. Okay? We go. Right in here. Right in here. And then I will solve these two equations in terms of the change of the magnetic flux, like that. The negatives, the VP goes to the right side, right? VP goes to the right side now. And the NP goes to the right side as well, like that. I'm going to pass the negative sign to the other side as well, right? And you do the same for the equation of the secondary circuit. And I just changed secondary here. Okay. And now we have this new relation that we didn't know existed. And this new relation is going to be what? This one is going to be equal to this one. Okay. Here you go. I will copy this one here. Those are one of the surprising results that we obtain in physics and engineering. We can build very reliable and efficient devices. So here you go. The negative sign cancels out. We're running out of time already, right? 10, 12 more minutes to go. The negative sign cancels. Here you go. I want to write that down in terms of the secondary voltage. So let me pass this guy here to the other side. Okay, so continue deriving. The NS is going to go to the other side. I'm going to put the ratio in terms of NP and NS. Oops. Yeah, go. NP and NS. BP. Here you go. VS. Like that. And now we analyze this relationship here. We analyze this relationship here. Okay? Suppose that NS over NP is 2. Okay? Suppose the secondary circuit has twice as much turns, twice as many loops as the primary one. Suppose, right? What does it mean? It means that the voltage, the peak voltage in the secondary circuit is going to be twice the peak voltage on the primary circuit. Make sense? Okay. Now, suppose that, suppose that would be a step-up transformer. Suppose NS over NP is equal to 2, right? This is a step-up transformer. Step-up transformer, right? Where did I put step-up transformer here? Here you go, step-up transformer. Transformer that increases the peak voltage. Now, suppose, on the other hand, suppose NF over NP is half, right? The voltage in the secondary transformer would be half the voltage in the primary transformer. That would be a step-down transformer. That's one very interesting result. Okay. Numerical example. We have 9 more minutes to go. Let's do a numeric example. Let's see. Let's take an example from real life, right? What is the transmission voltage in real life through a power line? So, in real world power systems, electrical power is transmitted through high voltage overhead lines at level ranging from 110,000 volts. Think about that, having 110,000 volts at home. Nobody would survive, right? To over 765,000 volts. We don't have that high voltage at home. The voltage that we have at home is at most 220 volts. We are talking about 1,000 times less than the voltage that's transmitted through the power lines. Here are the power lines. Electric power transmission. Okay, so, and we want to bring that down to 120, 110 volts, right? Or less. Or 220, not at most 220 volts. In factories, they have even 330 volt voltage. Okay, so let's take a look at, we have this numerical example that deals with those numbers as well. Here you go. Step down transformer example. Primary voltage, 240,000 volts. Exactly the number that he cited here, right? Within the range, not exactly the number, but within the range. 110 kilovolts to 765 kilovolts. So my example is 240 kilovolts. So the primary coil has 1,600 turns. The secondary primary coil is the one that's connected to the generator, right? The secondary coil has 200 turns. Find the peak voltage in the secondary circuit. Solution. All right, so we go use the same equation. The equation that we have is this one right in here, or this one. See, we want to use this equation here. Fine, we got solution. Here you go. Use this equation. What time is that? 6 more minutes to go. Let's use all time that we have in our hands. NS 200 turns and P is 1600 turns. VP is 240,000 volts. Will we be able to go down to 110? It doesn't look like, right? Yeah, it doesn't look like we're going to be able to go down to 220 or 110. Yeah, in order to go down to 110 or 220, we need a ratio here of 1,000. Yeah, that's what we need, a ratio of 1,000. So here you go. This one here is going to be 1 divided by 8. And now we divide 240,000 by 8, and we get 30,000 volts. Okay? That's what we have for the voltage in the secondary circuit. What about the current in the secondary circuit? Right? What about the current in the secondary circuit? Four more minutes to go. And let's see, I want to make sure we cover power. I think we did, didn't we? Power outage. Power. Well, let me write it down. The power, electric power. Okay, yeah, that's it doesn't look like we covered yet, but it's not difficult to talk about it because the equation is very simple. Electric power. Let's see. Oh, it looks like I did. Yeah, I did it. Okay, I covered back there. Remember this equation, right? Three different equations for the power in an electrical circuit. P equal to VI, P equal to VR is V squared over R, and there must be a third equation not also. V squared over R. Well, just remember that. We're going to use this one here. There's a third equation, okay? I'm not going to struggle with that. Ri squared. The third equation is Ri squared. Let's write that down. Let's write it down there. 2 more minutes to go. To get the current the secondary circuit, we don't use Ohm's law. Actually, we do use Ohm's law in an indirect fashion. We use Ohm's law through the power, right, of a circuit. So here you go. One of the equations for the power is VI. Power is VI. Ri squared as well. That's another way. And another equation for the power is this one right in here. Three different equations for the power using Ohm's law. Okay, so since transformers are very efficient devices, okay? Their efficiency is on the order of 95%. Is on the order of 95%. Okay? The power transmitted from one circuit to another conserves. Okay? So we have the following equation, right? Power on primary circuit is equal to maximum voltage in the primary circuit times the peak current in the primary circuit. Power on the second, I should put capital, right? Capital P here. I'm gonna leave that, otherwise we're gonna run out of time. Here you go. Secondary. Okay. Here you go. What else? Conservation of power between the two circuits. It's gonna be P in the primary is gonna be equal to P in the secondary, right? And then we get this relation here, V secondary times current in the secondary is equal to V in the primary times current in the secondary. So here you go. So the current in the secondary circuit is going to be something like that. Something like that. Okay, V in the primary divided by V in the secondary. Let's see here. V in the primary, blah, 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 V in the primary is NP over NS, right? NP over NS. So let me copy that. Oh, we ran out of time already, but we still have office hours. So here we go. I copied this one right in here. And we get finally the current in the circuit. Here you go. Okay. That's what we have for this chapter. We're done with chapter 22. We covered everything we want to cover. And I will see you Wednesday for the next lab meeting. Okay? Thank you for attending here today. We have office hours right now. Stop the recording.